Welcome to today's Explainer. Today, we're diving straight into a huge breakthrough, how modern AI systems are finally learning to read complex visual documents. I mean, we hear constantly about AI reading text, right? But out in the real world, our data is absolutely packed with charts, tables, and diagrams. So how do we actually build systems that can see and understand all of that? Well, that's exactly what we're going to demystify today. I want you to start by asking yourself a pretty basic question. What happens when your AI can't see the charts? It's a massive critical blind spot. Most standard AI setups completely miss visual data. Think about it. If you hand a traditional AI a 50-page report, it might read the text flawlessly, but it is completely blind to the bar charts, those intricate graphs and the complex tables that, let's be honest, usually hold the most important numbers. It's literally like trying to read a science textbook with all the illustrations ripped right out.
So here's our game plan for today. We'll start with the traditional RAG problem, introduce multimodal RAG, explore the two-store system architecture, look at processing images in tables, walk through a real-world wildfire example, and wrap up with some limitations and takeaways.
All right, let's jump right into parts 1 and 2, the traditional RAG problem, and enter multimodal RAG. Look at the stark contrast here. Traditional RAG is strictly text only. It completely ignores visual data. But multimodal RAG, it essentially acts as the AI's eyes. It captures text, tables, and images and processes them all together. By capturing every type of information, the AI can actually cross-reference a paragraph of text with a bar chart to give you a significantly better, way more accurate answer. It's a total game changer. Moving right along to Section 3, the two-store system architecture. Let's trace this end-to-end data flow. Your raw PDF flows right into an extraction engine, something like unstructured.io. This engine does the heavy lifting of splitting the document into text, tables, and images. From there, the data actually splits into two separate databases. The raw full-fidelity files go into a document store called Redis, while short, search-optimized summaries are sent over to a vector database called Chroma. Finally, when you ask a question, the relevant pieces are retrieved and fed straight into GPT-4o to generate your final answer. So the really crucial thing to understand here is that this pipeline operates in two totally distinct phases. Step 1 is the indexing phase. This happens completely offline just one time per document. You extract the data, summarize it, and store it. Then step 2 is the query phase. This happens online, in real time, every single time a user asks a question. The system searches the summaries, pulls out the raw text and images, and generates the answer on the fly. Now, the brilliant glue holding all of this together is something called a multi-vector retriever. Honestly, just think of it like a physical library. The vector database, Chroma, is your small card catalog. It's incredibly fast for searching through short summaries. But once it finds the right card, it uses an ID link to point to the document database, Redis. Redis is the actual bookshelf holding the full, heavy, rich, raw data, like the high-resolution image of a chart itself. So you search the tiny summary, but you retrieve the full original file. Pretty clever, right? Okay, Section 4, Processing Images and Tables. Let's look at tables first. When extraction tools pull tables out of PDFs, they usually spit out really messy HTML code. And large language models, they can really struggle with raw HTML. But by converting that messy HTML into a clean Markdown format, we basically empower the LLM to easily understand the row and column relationships. It can clearly see, for example, that in 2020, exactly 17,904 structures were burned. For images, well, it's a bit more complex. We take the extracted image file, say a JPEG of a graph, and we encode it into a text string format called base64. We then pass that base64 string directly to a vision model, like GPT-4o. The model looks at it and generates a highly detailed, search-optimized text summary of the image. It actually reads the axes, the data points, the trends, the whole shebang. Suddenly, a previously unsearchable picture of a chart becomes a rich paragraph of text that our card catalog can index perfectly. Let's bring this to life in Section 5, Real-World Wildfire Example. Imagine a user types in this exact query. Tell me detailed statistics of the top 5 years with largest wildfire acres burned. Now, to answer this properly, the system absolutely cannot just look at one paragraph. It has to retrieve a text passage on historical averages, a markdown table of annual fires, and most importantly, an image of a bar chart showing the top 5 years by acreage. The AI literally has to reason over the text, the table, and the chart all at the exact same time. And you know what? It works beautifully. The system flawlessly identifies 2015 as the #1 year, reporting exactly 10.13 million acres burned. And here's the kicker. This number wasn't just explicitly written out in some plain text paragraph somewhere. It was extracted by reasoning across the visual chart and the surrounding data. It perfectly showcases this precise extraction capability from visual data, something that traditional RAG would have just completely ignored. All right, finally, Section 6, Limitations and Takeaways. If you're actually planning to build this in production, there are definitely a few hurdles you need to keep in mind. First up, that multi-vector pattern. Searching the summary but returning the raw document. That is the core trick making this whole thing possible. Second, because you are relying on searching summaries, high-quality summaries are absolutely your biggest lever for success. Bad summaries mean bad retrieval, period. Third, remember that a model like GPT-4o is actually being called twice, once offline to summarize every single image, and then again online to actually answer the user's question. Because of that double hit, you've got to keep a very close eye on API costs and rate limits. And lastly, if you build this, you must add proper evaluation frameworks and safeguards to handle things like empty search results, stuff that basic tutorials almost always leave out. I want to leave you with one final, kind of provocative thought. We just talked about converting images to base 64 and sending them off to GPT-4o to be summarized. But what happens to your data privacy when highly sensitive proprietary document images are sent to external cloud APIs for that summarization? I mean, if your PDF contains regulated financial data or personal medical charts, the real-world security implications of passing that visual data outside your secure network are massive. It is an incredibly powerful tool, for sure, but it's definitely one that demands some really responsible architectural choices. Thanks so much for joining me on this explainer, and keep learning.